Hello, fellow Haskellers, and hello, Torsten. How are you?
Hello. I'm very good, thank you. Thanks for being here. Thanks for allowing me to be here. That's the
Well, it
first
was your
time
idea.
I'm here on this channel.
So, since it was your idea to stream the work we've been pairing on for the last few weeks, why don't you tell the audience what it is that we're working on today?
Yes, so a few days ago, we started working on a little HaskTorch project. So HaskTorch is a library for tensor manipulation, so tensor math in Haskell. And it is well, it's a foreign function interface actually to libtorch, which is also powering the PyTorch framework in Python, which a lot of people use for the machine learning and neural network research and production stuff. But this library is written in Haskell, and it aims to be, it should look familiar to people who are familiar with PyTorch, but it also should look familiar to people who are used to Haskell. It sits somewhere in the intersection of both. And the project we carved out for us is called Haskell Mask. It's a project we're trying to pull off where we are taking a so-called BART model, which is a machine learning architecture that has been pre-trained for us. And we're trying to make it run in HaskTorch first before we use it to do interesting program synthesis stuff. But yeah, so like we're taking small steps here. The first objective is to make this model work in HaskTorch. So there's not yet an implementation, excuse me, of it, but we need one in order to run it. So last time we looked into a component of that model called multi-head attention. And yeah, it's displayed right now. So basically, multi-head attention is a low-level component of that BART model. And we had already an implementation of multi-head attention to work off of. But the BART one is slightly bit different than the one we had. So the multi-head attention that is already in HaskTorch is made for a different model called T5. This one is for BART. And you can compare the two. There's not much different, but there's some small but important differences, and we took care of those. And today, I guess we move on to self-attention and cross-attention, which are special cases of multi-head attention, if you will.
Okay. So what does this diagram mean? Are there like parts of that diagram that will be different in those specialized versions?
Yes. So which one are you showing actually here? You're showing the one for multi-head attention. So this is the one that I think was already in HaskTorch. And in this one, we have 4 inputs. There's attention bias, query, key, and value. And then different things happen to them before they're combined and produce a query as an output, or a new updated query as an output. And then in self-attention, we don't need key and value. We only have attention bias and query. And we're using query actually instead of key and value. So that's the difference. But we don't need to re-implement the whole thing for it. We can just take it and wire it up so that it does the right thing.
So instead of receiving a query, a key, and a value, it will receive... Is it the one that receives one thing that is used for all 3, or does it receive 2 things?
It retrieves the first 2, attention bias and query. And we're gonna just use query,
so then the query will
instead
be used
of key and value.
As the query,
Yes.
the key, and the value. Okay.
Mm-hmm.
So you want me to scroll somewhere else?
Yeah, so let me open actually the self-attention file. I wonder if I do that, if you're taken there too. No, you're not. I think you have to activate following mode again for this.
It's fine, I found it.
You found it?
Yeah, you're in the selfattention.hs on line 43, import torch, gradually type dtype. That's probably not the part you want to show me though.
I think I'm actually in the 300s in terms of line count.
Now you are. Like I think when you scroll, it doesn't show me where you are. It only shows me where your cursor are. So you have to click around so that I can follow the yellow cursor. But now I do see the diagram. Attention bias and query.
Yeah, so it looks somewhat similar to the one we started before.
That's similar. There's a bunch of steps that were missing. Like there were like projections and reshape and something else. I don't see either of those things.
Yeah, that's because they have been refactored or like absorbed into this SA multi-attention thing that lives in the middle.
Ah, so the entirety of the diagram we just looked at would be incorporated here in the SA multi-add attention, and that's why it receives the same four things we just looked at: the attention bias, a query, a key, and a value, which are the query. So that means we're doing something to the query before we are using it as those three things and reshaping and projecting it and so on. So what is this layer norm thing?
Right. So I said like we only need to query. Let me rewind a bit to explain this a bit better. So the structure that we're using here is the structure that is used in the T5 model, where there's multi-attention, which is the most generic form of attention that we're gonna encounter here, and then we specialize it to either self-attention or cross-attention. So cross-attention we have not yet seen, but we're now looking at self-attention. But there's a twist. We not only, when we talk about self-attention, we're not only talking about the specialized multi-attention module. No, we're also talking about two extra pieces, which are this layer norm thing, which is just a thing that normalizes inputs in a special way. And T5 uses a bespoke version of it, but we won't use that one, we will use a different one anyway. But then we also have dropout, an additional dropout piece. And then there's also this bypass that you see on the right. So there's this, so like the query goes in, and then there's the split, right? There's a left piece and a right piece. The left piece goes into first the layer norm and then the multi-attention. And the right piece goes all the way to the bottom where it says add. And then this is combined with what goes out of this
so the attention doesn't give us the new query, it gives us like a delta that we can add to the query. Presumably it can be negative as well.
Yes, okay. Yeah, you can think of it that way. Yeah.
Okay.
So like this is called the residual connection.
Okay.
So you can ask now lots of questions. Why this weird thing? Why do we need this?
I do want to ask a lot of questions. So, because like in our last session, I think that you explained a lot of high-level things that helped me to understand what it is that we are trying to accomplish, and I was hoping that you would recapitulate those for the viewers, but I feel like contrary, like we're already like deep in the weeds.
We're really deep into things already.
Yeah, so like the high level goal is we want to train the kind of language models like BART that is typically trained on English, and we want to train it on Haskell code because we want it to complete Haskell code instead of completing English sentences. And currently our hypothesis is that there's enough information in like the names of the functions or maybe the comments that we would be able to reuse BART's understanding of the English language, and so we're trying to reuse the weights of an already trained model that somebody else spends the CPU time to train, and we want to start from that and to after that further train the model in order to make it understand Haskell code as well as English. Did I summarize that correctly?
Yeah, that's exactly it. You could, of course, ask, well, you're going through all this trouble now, re-implementing that model. You already have a transformer implementation on HaskTorch. Why do you need a second one?
The T5 model you were talking about?
Yeah, exactly. So over the holidays, I made a T5 implementation, which already works. And you could just go with that one if you wanted.
If we were training from scratch.
Yeah, so like if he's trained from scratch, you may want to use the T5 one. But since we have decided to go with BART for this experiment or for this project, for reasons I can go into later again if you want, but we need to modify the already existing T5 transformer to one that understands BART, right? So I mean, if you squint, they're really, really alike, right? So like they all follow like the standard Waswani et al. Transformer encoder decoder plus cross attention pattern.
Yeah, the architecture is very similar, but they have been trained on different tasks, and I think that's what makes BART more appropriate. It's been trained on the task where you mask some parts of the input and the model is trying to guess the missing words, which, by the way, that's why the show is called Haskell Mask, because you're supposed to get that it's Haskell cat. Anyway, but the T5 model, if I understand correctly, it's been trained on like 5 different tasks, like probably something like classification or translation or something like that, that doesn't really fit our task of filling out some Haskell code, and so I think that's why BART is more appropriate.
Yes, so that's at least the assumption for now. I mean, we may try BART and then get mixed results, and then maybe we want to try T5 as well. If we have both, we can do that easily, right? So but I think at the moment it makes more sense to work on BART. And I think it's also a nice exercise apart from that, and a little bit about how we can write these models in HaskTorch. So like a little disclaimer here. So like a user of HaskTorch will probably never have to do what we are going through here. And that's just because like these pieces are kind of like available to users. It's rarely that actually users have to kind of like implement their own versions of those, right? They're like these standard architectures, and typically you just rely on these things being available. You're not really in the business of making up your own transformers, right?
Oh, really? I thought that a big part of the machine learners' craft was to pick an architecture that was fitting well for the task. Are transformers so good that this is no longer the work of the machine learners' job? Now they just always use transformers for every task.
As a researcher, yes. So as a researcher, okay. This is your livelihood, and this is why all these different models exist, right? So there's not only BART and T5, there are tons of others. But there's this pre-training bit, right? And for pre-training, you need to have deep pockets, meaning that that costs a lot of money because you need to train this on a lot of hardware and big clusters with a lot of expensive pieces, GPUs, TPUs, what have you. And also you need the data to do so, right? So like all this like crawling the internet and preparing the data and cleaning it up, right? So it takes a lot of time, lots of resources. These models have become popular because all of this is already done for you, right? And then the thing is like if you make changes to their architecture, right? So like if you decide, I don't want to have a layer norm here, I want to have something else or nothing at all, or why have to bypass here? Why not I don't know where, right? You would break the model. Like the pre-trained snapshot would just not work anymore for you, right? And then you have to start from scratch. So typically these changes, while they happen, they're not as frequent, right? And what we're doing here is kind of like groundwork for people who want to use this library. Um, and, uh, and I think I'm also saying this because a lot of the things that are in this file, it's quite a long file, and there's a lot of type shenanigans in there. That's things that you may want to look at, you may want to spend some time on to digest, but it's not something you want to as an end user, mess with all the time. You don't need to either. That's
Well,
just
I
my
don't want
disclaimer at the
to
beginning. So like if somebody
mess.
looks at this and says, oh my God, HaskTorch is so super complicated. Oh my God. No, like in the end, there will be one call to this model. It will read forward BART, and that's it.
That's good. I don't plan to mess with the architecture, but like you went through the trouble of drawing those diagrams, so I would like to understand the architecture that we have re-implemented or are re-implementing. Are we done with the converting from T5 to BART? We did some of the work last week off stream. Is
Yeah,
there
so
more work remaining?
yeah, there is more work remaining. So I made these string diagrams over the last few days, not only for these little pieces, but all the way to the final model, almost at least. I ran out of a bit of steam at the end, but there's some minute differences that we have to take care of. So it turns out that where this layer norm piece is that at the moment is poorly understood is different between T5 and BART.
And that's why
And
we have the BART Python implementation on the right, so we can
yeah,
compare the implementation and spot the differences. So where would be
so,
we find layer norm on the right here? Can I just search
yeah,
for
so
norm?
right, so it's a
Layer
bit
norm.
tricky to see because so on the left where we have the Haskell code, I said earlier before I followed the T5 pattern I found in the official source code, which happened to look like exactly that. So like the blocks, or like basically there's a hierarchy of PyTorch models implemented. I just re-implemented the same hierarchy. Turns out though that in the BART source code that's on the right, that hierarchy does not exist as clearly.
Just to clarify, by
But
hierarchy, you don't mean like the diagram we're seeing on the left, but rather that there is both the self-attention and the multi-head attention, and those two are related? That's the hierarchy you're talking about?
yes and no.
Okay.
So there are other modules in that file, sorry, in that directory, and they're like called block, stack, and decoder block and decoder stack, and so on. I'm talking about this hierarchy. So like a block contains self-attention and a feed-forward network, right? And so like there's this hierarchy of well, like basically there's this nestedness of modules.
Do you have
Of
a
models.
diagram for the overall picture?
Not of the overall, that would have been quite clumsy and big. But if you look into block.hs, I'm there right now. I see it on the left, under BART.py, block.hs. Yeah, exactly that one. If you scroll down to line 150 or so. Yeah, so you see like a block is self-attention followed by a feed-forward network, right? So whereas self-attention is exactly what we looked at before. So like you have this nested structure, and in the BART source code that is on the right, we don't have that nested structure as explicit as it is in the Haskell source code. But it follows the same, let's say, flow, right? It's just not nested.
Yeah, so we'll need to mentally expand the abstractions that exist on the Haskell code into a flatter kind of network, and then see if it corresponds to the flat description of the network on the Python code on the right?
I think so, yeah.
Okay. And
but I think we were looking at self-attention, so maybe we start there.
well, I would like to understand the bigger picture because like you are now telling me that there are those blocks that contain attention blocks and feed-forward network, and while we could be just going line by line and comparing and seeing if the words on the right correspond to the same words on the left, I think that would be much more interesting if I understood what those words meant. So,
okay.
Like the architecture, like what's the biggest component? Is it those blocks? Is it consisting of a series of blocks or something?
Okay, so I don't want to go to the highest level just yet, because there are some external pieces that we need to fold in too, and they're a bit different for T5 and BART, and that would be confusing at this point.
Okay.
So I'll start a little bit inwards. So there is an encoder and a decoder.
Yeah, we've talked
These
about
two
that
pieces,
at length, but yes, let's explain it to the audience.
Right. Sorry, I go on, or is there? Okay. So there's an encoder and there's a decoder, and the encoder takes the input, encodes it, it's in the name, and then the output of the encoder is what is given to the decoder. And both encoder and decoder are made up out of a stack of layers. And typically the number of layers in each stack is the same for the encoder and decoder. So like, I think for the smallest BART model, it's kind of like 6 layers, I believe. In both cases.
But you're again like going into the weeds before explaining the big picture. So let me try to summarize my understanding of the encoder and decoder from what you've told me at length in the previous sessions. So the encoder takes as input like the text, like English text in the case of the BART's pretraining, but eventually we want to have some Haskell code. You told me it's not exactly the text that has been like converted into tokens, but whatever. It takes a sequence of tokens that represent the text, and it crunches it down via those several layers into some more semantic representation of the text instead of just the syntax. And then this information is passed to the decoder, who now understands the semantic of the sentence, but it now needs to output something, and there's a variety of tasks in the case of T5, like outputting what is like the classification, if it's a happy sentence or a sad sentence or whatever. Or it could be to output just the same sentence back out. And that's what we want, because we want to generate some code, so we want to generate back the same input. So in the simplest case, we have one input, it's crunched back to the semantic, and it's output back into the same code. But what makes this useful is that if the input contains some holes, it gets crunched to a semantic description that is apparently sufficient for the output to recover the same sentence without the holes. Because that's what we want. We want to complete the holes, the masks. Okay. So now that I've explained the overall picture of what the encoder and the decoder mean, so they're both made of 6 layers, you say. So what do those layers do?
Okay, so when you said high level, I didn't know you wanted to have the semantic explanation of what's going on. I thought you wanted to have the how the data flows basically through the model. But let me comment on the semantics a bit. Right. So like, okay. So like you said, like, okay, there's some weird step where sentences or even words are chopped up into tokens. Yeah, so that's just necessity, because somehow you need to convert words into numbers, right? And So what's happening is there's an algorithm, it's called a tokenizer. And in this case, we're using a tokenizer called sentence piece. And the tokenizer has been is an algorithm, and that algorithm has certain objectives. And what you can do is, like you say, here algorithm, I give you 40,000 positions in a big vector, and you now find the optimal split of all the words I have in the training set, such that you only use 40,000 positions, 40,000 different tokens.
Using
But
something
in a
like
way
Huffman
where...
encoding?
Pardon?
Using something like Huffman encoding to use short codes for very common pieces?
You can think of this way, yeah.
Mm-hmm.
Right, so like what happens though, like at the end, basically things that are more frequent in the original text are more likely to appear in this vocabulary as whole words, right?
Mm-hmm.
So like, if you look at the English language, there's some words that are very frequent. And even though they may be long, right, still there will be a token just for that word.
Okay, so unlike the Huffman encoding, it's not that the common word has a short code. All of the codes have the same length, but we can encode a frequent but large chunk into a single token. Whereas if there's a sequence that is very uncommon, then maybe it will have to be split up into a large number of tokens that are maybe individual letters or very small.
So for instance, if you had like a hash, right, in your data set, which is just like seemingly random occurrences of alphanumerics, then probably the tokenizer would go and chop this up into pieces of just one character, right? Because most likely any of these successions wouldn't appear in an English text, right? So like there's no point of like exposing this as like one big piece. And the reason for that is plainly because if something appears only once, right, there's not much information there that you could learn about it, right? Like in the context, right? So so it makes sense to chop this up into smaller pieces, because maybe these smaller pieces appear in more places, and then you can maybe learn the semantics of each of these smaller pieces, right? I don't know if the audience knows about German language a bit, but maybe like by osmosis they have seen that like in German you have noun composition a lot, right? So like you build up words. I mean, you have self-attention here, right? Self-attention. You can think of this like two nouns or like two words to glue together, right? And maybe the tokenizer would split this up into self and attention, even though here it's written as one word. But if self-attention, if your whole corpus talks a lot about self-attention, maybe it keeps it as one piece, right? Because these words when they appear together mean something else, right? But actually, the tokenizing algorithm doesn't know about that, right? It doesn't know about the semantics. It just like exercises this sort of heuristic. And the semantic or the understanding component comes only into the picture once we look at the model itself that uses this stuff as input. So actually for each of these tokens, we have an embedding vector, right? So like each token has an ID, and that ID is basically an index to go into a big matrix of vectors.
Oh, so we're not sending the numbers as the input to those layers. We're sending vectors like in some space. So those tokens are already mapped out using like something like word2vec. We know their relationship to each other in some space? Or are the vectors just one hot?
No. So like you could start with a pre-trained embedding. People nowadays actually the embedding is trained at the same time as these models themselves. Excuse me. At least originally, like BART starts with a untrained embedding, I believe. So that means it's basically at the beginning, before training has started, it's just like normally distributed numbers. And I don't know how many there are per token. That is actually a hyperparameter, and it depends on the version of BART that you have. If it's like the base version, the large one, the extra large, what have you, how many numbers there will be per token. But we're talking in the order of hundreds.
Okay.
So like a 40,000 by a few hundred matrix is actually quite large.
So each token is represented by a random point in a big n-dimensional space. Okay.
Yes, originally yes, but of course, due to training, this becomes less and less random, and things that mean similar things, they will probably be more closely together.
Because it's not just the weights of the layers that transform those vectors that are being trained. It's also how we choose to represent each token, like the position of the point in that n-dimensional space is also being moved around using backpropagation. Okay, cool. Now that's the kind of semantics I wanted to learn about. Okay, thank you.
So that first step of this like big lookup table of vectors. So that's the shallow embedding, and now with these models, we have these n layers, and that's in the deep embedding, right? That you do. So when you hear the word or expression deep embedding, you have to separate it from shallow embedding, which is basically just this initial encoding, and then later on we look at. So the difference is of course that the shallow part, right, doesn't know anything about context. It has a series of numbers for each individual token on its own, right? Mm-hmm. Although these things have been trained on a corpus where there is context, it's just a big lookup table, right? Mm-hmm. And building a contextual representation is then the job of the model, meaning that when you have a sequence then of tokens, you can construct a representation of each token in the context of the other ones in order. Yeah, that's the difference. And then when you go through the model and the layers, the contextual representation that emerges becomes more and more, I would say, high level. Like it becomes more and more semantic the higher you go. And that's just a property that these models have. And I wouldn't be able to comment much about why that is. I think there's a lot of, I mean, maybe this is not no, but I don't have a good answer. I mean, it's this emergent property of these models, right? You typically see that like at the lowest level, we have basically interactions just between closest neighbors, right? Mm-hmm. Not because like larger neighbor interaction is more costly. It's more like you tend to find that like there are more like surface level interactions going on at lower levels, and the higher you go in your layer stack, the more complicated features will become part of that representation. So maybe you have something about negation at some point, right? And then the higher you go, maybe you have something about sentiment or I don't know what, right? So not good, right? First you learn that not good means the opposite of good, or right? And then the higher you maybe, the model becomes aware that not good is actually a sentiment that is negative, right? Mm-hmm.
So you keep saying higher, presumably to mean higher level, but in the diagrams, like the data flows down. So presumably if we draw the data as coming from the top, we'd have the 6 layers of the encoder, and we are lower and lower in that graph the more higher level we are, right?
Yeah. So okay. Yeah. That's a bit of unfortunate habit of the community. So like typically when you look in diagrams in the papers, the input is typically at the bottom.
But in the ASCII diagrams we're looking at, you wrote them the other way,
this
right?
is because I'm reading from top to bottom. So okay. I'm normal. The literature is not normal.
Okay.
Right. So, but like when I say from bottom to top, it means like from the input towards the output, right? Mm-hmm. So like the encoder gets as input um, numbers, which will be indices into a big lookup table, which goes to the shallow embedding. From there, you feed this as inputs to the first self-attention layer of your model, which lives in a block, and then a stack of blocks goes higher and higher. So this is kind of like how people talk about that. And why they start at the bottom and end at the top. Probably it's because of this sort of like emergent property that I was talking about. Like when you talk about it, you tend to talk about bottom and top, right? Or high level and low level, right?
Yeah,
Features.
that makes sense.
So maybe it's because of that.
So you just mentioned blocks. So are we finally getting back to the code on the screen? We have those 6 layers. Are those 6 blocks?
Where are you looking?
Block.hs?
Yeah, exactly. So the way I've implemented this is there's the stack, and the stack contains n blocks. And each block is, for the encoder, I'm looking at now the encoder blocks, is filled with 2 pieces. First, the self-attention layer, and then followed by the feed-forward network. And it's really important that this query goes in, query goes out is always fulfilled, right? So like because
so you can stack
between a sandwich,
n of them, yeah.
Stack, right? So the input and outputs they need to be lined up.
Wait, but the queries are lined up, but this attention bias is not? Does this mean that this consists entirely of weights that are being trained and not data that is then being fed to the next layer?
What is that?
Well, in the
Attention
diagram,
bias.
there's 2 inputs to the block, the query and the attention bias. And you are just talking about how, it's important that the input matches the output, so we can make a pile of them. We can feed the output of the first into the input of the next, and like basically do a function composition.
Right. So like the iterative notion of the stacking, right? This is just the query part. You can think of the attention bias. Now we're in Haskell, so we can use that nomenclature or these terms. The attention bias is kind of like the reader monad here, right?
Okay.
So like it's basically this thing that you just, it never changes actually from block to block or from piece in the ladder. So it's always the same attention bias. And it's only used by the self-attention module, not by the feed-forward thing.
Okay.
So there's additional things you feed in, but they're unchangeable for the purpose of the encoder.
Cool. So now we're going deeper and deeper into the details. Have we reached the level of detail where we can write some code?
I would hope so. But I forgot where we were.
Well,
so
eventually
look at self-attention motion.
What?
Sorry, didn't get that?
Eventually, we want to compare the Python code on the right to make sure that it corresponds to the code on the left, or at least like that the expanded out version of the code on the left, if we expand all of the abstractions, correspond to the code on the right. So is block well, that's one of those abstractions. So I guess we would not find a block on the Python code on the right. Is that correct?
No, unfortunately, if you used full text search on the right and you just search for block, you would not find it, I guess.
Okay.
But I can take you to the point where I think we get sufficiently close to what the block is. So let me do that quickly for you, and then I yeah. So I think I would send you to line 304. No, why does it say I'm there? I'm not there. I'm in line 304.
yeah, you're on line 304.
Oh, okay. I think it was because of the lag that I was confused. Yeah. So you see there is this residual thing that's been assigned hidden states. So hidden states is what the Python code refers to as the query. So when you read hidden state, think query. And then you can see there's this call to self-attention. And then afterwards you have dropout.
And I remember seeing dropout inside of one of the other modules.
Yes.
This one here, self-attention. Excellent.
Then you have residual plus hidden states.
Yeah, that's this add.
Yeah, and then afterwards you have self-attention layer norm.
Oh, so the layer norm should be after, not before.
Exactly. And then we go into the feed-forward part. So then again, some new residual, again, assigned initial to hidden state. So this is for this bypass thing, right, that I mentioned earlier. And then we have a succession of first FC1. So FC stands for fully connected. The word I used for that was, I think, input something.
I'm confused. You're saying that we are now looking at the bypass, but I thought that on line 312, when we were adding the residual plus the hidden state, that is the query, I thought that was corresponding to when we add the thing that has been computed by the multi-head attention to the original query.
Yeah, so maybe to make this more clear, you could open not the block on the left, but the self-attention?
Yeah, that's what I'm looking at, self-attention.
Okay, and then, yeah, you see this residual connection, and this is exactly the one you alluded to.
So that, but does that correspond to 312 or 320?
Yeah, so I think what we're looking at in the self-attention.hs, this corresponds to lines 304 to 313.
Okay, so in the block after the self-attention on lines 304 to 315, there's a feed-forward network. So are lines 315 to 321 corresponding to that feed-forward network then?
Yes. So I'm going to the feed-forward network file right now. And if you look in lines 202 and following, there's another little diagram. And
and I see a bypass and an add. Excellent.
So there are two bypasses in this little module there. So there's one around self-attention and another one around the feed-forward network.
Okay.
But can you do the little spiel from before and tell me if you see any differences between what we're seeing in the Haskell code and what we're seeing in the Python code?
Sure. Okay, so we begin with the query called hidden state. It names it residual, I'm not sure why. And then layer norm, I don't see a call to anything called layer norm, but maybe I just don't see it. Let's search for norm. Yeah, I see layer norm at the end rather than the beginning. Oh, but I see a call to layer norm at the beginning of 312. So I think in both cases, it does the layer normalization at the end instead of at the beginning. Like we're doing it at the beginning on the Haskell side, and it's doing it at the end in the Python side. Any other differences? The input weight. Wait. So I do recognize the word dropout on the left that occurs at two different places on the right. One of those is the ReLU dropout and the other one is something else. I don't know how to distinguish those two. In the middle I see a thing called FC2, whereas in the middle of the diagram I see something called ReLU. Is FC2 how PyTorch calls ReLU?
No,
or are they distinct?
Let me clear this up for you. So indeed, layer norm is in Haskell or HaskTorch at the beginning, and there it is at the end. And then if you go further into the Haskell side, the next thing would be input weight, right? And then on the right we have FC1. So this is a bit weird because it's the argument of this extension underscore FN. But FC1 is actually input weight. And FC stands for fully connected. So this input weight thing on the left in Haskell is actually a linear transformation weight. And on the right, it's referred to as fully connected network. So these two terms are interchangeable. You can either call it a linear layer or a fully connected layer. This is the same. And the next thing in Python is activation function. Well, activation must go fn. On the left in Haskell, we have relu. So the difference here is that in the BART code, the activation function is configurable. So you can choose which one you want to use.
Makes sense.
But on the left, we decide, or hard code is to be relu. The thing is just that in all my encounters, I never saw anything but relu, at least like for these more like common architectures. So my guess is that activation function is indeed also relu, but we need to check. And then next thing is dropout. Well, this is called here f.dropout, but then the argument of that is p equals self activation dropout. So our thing on the left is called relu dropout. So that's just that's dropout again. Then we have output weight in Haskell and FC2 in Python. So that's again basically linear transformation, exactly one. And then we have another dropout. And these are completely lining up between the two code bases. And then there's the add in Python and also in Haskell. But then, of course, the layer norm is in Haskell because it has occurred in the beginning, right? But other than that, it's kind of the same.
So you listed a whole bunch of things. So okay, so we need to move the layer normalization to the end, but the input weight is defined. Relu is probably the same, but we need to check. Relu dropout also the same. Output weight also the same. Dropout also the same. Add also the same. Okay, and the layer normalization is after the add. Okay, so presumably after this comment, there is some code that will talk about layer normalization. Here. Layout normalization. So can I just move that to the end?
Wait. Please don't change the code.
Okay. Sorry, I thought we were fixing things.
So we're not over. I mean, we're not. What we don't want to do is like you don't want to like undo the T5 in order to support the BART, right?
Oh, this is the T5 code. Okay.
Yeah, you just changed the T5 code. But it's fine. Like, but what
I undid the change.
You did was not wrong. It was just so like also I looked up BART, and it turns out the activation function is not relu, it's gelu, spelled with a G. So there's a different activation function, and actually we have to find out where it is in HaskTorch. Maybe already implemented. If it's not implemented, then we have to do something about it. But we can also do that another time because it's a bit of a nuisance at this point, and it's not really that important for getting the
I would like to begin by moving the layout normalization to the end because that seems like an easy step that I hope I would have done correctly if this was the correct place in the code to do it. So I see BART feed forward network immediately below. So I'm guessing. Oh, indeed, there's a different diagram where the layer norm is after. Cool.
Yes. But I have to change this diagram because I wrote relu here. I want to change this into jello just to keep a mental note of that this is what we need to do eventually.
So I'm guessing I need to copy this whole thing.
Yeah, hold your horses.
Okay.
So I was thinking, actually, if you go to the very top of that module, right, you can see that there is a data definition. And the way HaskTorch works is you always define these forward functions for a data constructor, right? So here, this forward function is actually an instance of a type class called HaskForward for 3 arguments, type arguments. The first one is always the model, second one is the input, and the third one is the generator. So the model in this case is the transformer feed-forward network. At the moment, this thing has one constructor, also called transformer feed-forward network. But what I was thinking is, how about we make a second constructor of that thing? And then just add another instance for this.
Can you explain why you want a new data constructor rather than a new data type?
Yeah, so this is, I mean, you can, yeah. So either we use a completely new data type, which is fine, I guess. We could do that. The alternative that I would propose is we could use a indexed constructor for the other one. So like we're already here in GADT land, so we may just use a type index to distinguish the two cases.
So you want to make the existing data constructor more general?
Kind of, yeah. Because transformer feed forward network sounds very generic to me, but it is a very specific one because it's the T5 one.
Mm-hmm.
But if you could kind of like, let me just prototype this really quick here. So let's assume we had a, let's call it style, right? And we had a data type transformer style, right? Let me just make this up.
Mm-hmm.
Data transformer style.
And are the two styles T5 and BART?
So T5 and BART. Bam. So of course nothing type checks anymore. But if you index it like that, we could just like have some type, one for T5 and one for BART.
Sure.
And then I hope this would give us a bit more code reusability.
Yeah, I agree.
Yes.
I'm glad you stopped me before I just blindly copy-pasted this huge chunk of code. But I suspect we'll still have to copy-paste that chunk of code because that's the instance, right? You want to give one instance for the case in which the index is T5 and the one in which the index is BART. But at least with that design, we won't have to also copy-paste this data type definition.
Yeah.
Okay.
So, but I think we need to first, I mean, if you do it that way, I think we should move this thing to the more prominent top level part.
Yeah.
I would propose we create a new module for that.
Sure.
Because I don't have any. So I would call this probably type.hs. And then
type.hs? We just called it transformer style. You don't want to call the module transformer style as well?
I suspect that eventually we need more things.
Okay.
But we could temporarily call it that. So I just copy paste this in here.
Mm-hmm.
Right. So now it's there. And then of course now it's not found anymore. And the thing, luckily, we use the Haskell language server, which is this really cool new thing. And I think it would work right now if this new module was actually already somewhere in the Cabal something file, Haskell Cabal. And I think it's not, and that's why this doesn't work. Let me just add this quickly. Type, right. So I don't actually know if you need to restart the Haskell language server. No, we don't. Actually do that yourself. You can click on transformer style, which goes squiggly underlined, and then you see this little, yeah, just go where I am with the cursor, and click on the lamp, and then it should be added. Yeah, cool. Right, so what I don't understand is why all of this code is
compared to my usual raw Vim plus GCI workflow. This is an advanced IDE magic.
Okay, so but we need to, I think we should rename this type constructor. I will just rename it T5 transformer feed forward network. And then the first thing would be to use
that those two constructors will take different arguments? Oh yeah, because one of them is a ReLU dropout and the other one is a JELU dropout. Okay, yeah, makes sense.
Right, so I think I need... so I need to import that too. And then the next step is to copy this whole type constructor, give it a new name, BART. So the thing is, I think BART stands for... actually, let me look up what BART stands for. I think the T is actually transformer. Therefore, I would not call this BART transformer feed-forward network, because it's kind of like monitor display or something. Why does the paper not talk? Yeah, I think it stands for bidirectional and autoregressive transformers.
Okay.
So,
BART
and I guess
feed-forward?
also, yeah, you could also say the T5. Probably the T stands for transformer. You could call it just BART feed-forward network. And of course, it needs a different type index down here. So BART. But I think now we have a field name conflict. So what I would propose is to add just B in front of everything.
Okay.
For now, at least.
And
then
also we want a JELU here.
Yep. So maybe also in the comment there. JELU. Yeah. So the thing is that T5 in general likes things without bias. So you see these linear layers there, and they're indexed without bias. And that's not because they're very fair. That just means they only have a weight matrix, but not a constant thing that's being added to the result of multiplying the weights with the input. But if I remember BART correctly, and we can reassure ourselves that by looking at the BART source code on the right, we have to look into BART attention for... No, we don't. We have to look into what they say for FC1 and FC2. The definitions of FC1 and FC2 are now important.
Where in the modeling BART.py are you? Oh, okay, yes.
Yeah, so yeah, I see your cursor now. So that says just linear. So I believe that the default for using bias is true. So when I actually hover over linear, it gives me a little doc thing, and it says bias. If set to false, the layer will not. Yeah. So the default is true. So that means for our BART feed-forward network, we will need with bias. Bam. And then there's this layer norm, and also the layer norm typically, actually always, unless it's T5, comes with bias. So also there, we'll probably change it into with bias.
So I'm hovering over the layer norm function on the Python side. I expected to similarly see a bias argument that would default to true, but I don't. I see a different flag that is a boolean equals true called element-wise affine. Is it like a different name for bias, or am I looking at the wrong place?
Just open the definition. So if you click on just command click on layer norm, you will be taken to the normalization.py file.
No definition found for layer norm. Oh, okay, it worked.
Perfect. It worked. So if this element-wise affine thing is true, then you have two parameters. And I think the default is that it's true, right? I'm not sure. Yes, default is true. And it's called weight and bias. So yes, we have
I'm not.
them both.
Yes. If element wise is true, then it sets weight and bias. Otherwise, it still creates parameters with that name, but it sets it to none, presumably meaning that there's no weight in the model corresponding to the weight nor bias? Wait, so that's more than what we were talking about. We were talking about whether there is bias or not, but this also determines whether there is a weight or not.
Yes. So if you set that to false, but they don't do that for BART, then the layer norm is not doing any affine transformation.
Okay.
In HaskTorch, we only can choose between with and without bias.
Okay.
So I don't know. I don't think we have to worry about that. It's just that like in the T5 case, everything is always without bias. The whole model doesn't have any bias terms anywhere for some reason.
But it does have
they made that decision,
an affine
and it worked for them.
weight for the layout norm step, both in the T5 and the BART cases.
Sorry, say that again, please. Who has what?
Both the T5 and the BART models use weights for the affine transformation in the layout norm step, which is why we don't have to change anything between the T5 and BART description on the Haskell side regarding the weights of the affine transformation portion. It was only the bias portion we had to change. Okay.
I'm now staring at this name T5 Transformer Feedforward Network. I would like to rename this to just T5 Feedforward Network.
I assume that there's some more IDE magic that can rename all of the occurrences in one click.
I don't want that actually.
Okay.
Because, we will lose track of everything because there's a lot of stuff. So with Haskell, always like the different compilation steps, I would assume, or like compilation levels. It's almost like you have to defeat the Haskell compiler in different levels versus level 0, which is just the parsing of the code itself, right? So like surface level code. So like, but then we go into the type checking phase, and right now Haskell doesn't like that we rename things without telling it other places.
But you don't want to fix the problem first?
But one step at a time. So I think the first error I see is in line 266. So that is just because we renamed the constructor, right? So the thing is, of course, we need two instances now, because we need one for where this transformer style, what did I call it? Transformer style parameter is T5, and another one where that thing is BART. But this one here is, of course, the T5 one. So if you rename this into T5, we will have to add the type parameter accordingly, which will probably... Do you want to change this into T5 and witness the glory of Haskell freaking out about everything that has changed?
Too much.
That reads now 5 transformer. Yeah. Okay, so what's next? Okay, so we now have another arrow. Oh, okay, so like this thing is also used in other places. Do you see this in line 108 and following?
108. I see your cursor. Yeah. Don't see an error there yet.
No, I see it already in red.
But I can already see.
Oh wait, sorry.
But there's going to be a whole bunch of those, right? Why don't you want to rename
so the
them all?
error is... Yeah, sorry, the error is a different one. I was confusing myself there. Can you undo the renaming you just did?
Sure.
Thank you. So this error here is actually, at least this for me, expecting one more argument to transform a feedforward network. So that's because we forgot
the data constructor. Okay.
Yeah.
So
it's a data constructor. So
T5.
we can use T5 here, but actually what I would hope we could do, yeah, so wait a minute.
More generic, so transformer style. And we add another parameter somewhere here?
No, wait a sec. So the first three lines there say 104, 105, 106, right? Has initialized linear without bias C. And then another has initialized linear without bias C, and then has initialized linear,
So since
layer norm without.
It's
yeah, so this whole block is already specialized to the case without bias.
Mm-hmm.
So I think
T5.
so I think we should just say T5 here for now at least. Maybe there's a way to refactor this later, but right now I don't think there is.
Okay.
And you have to put the T5 everywhere. Yeah. Cool.
Right.
So I think there's this instance here for initialization. We haven't talked about that at all. So we don't only have forward functions, we also have initializers for these models.
Mm-hmm.
So that's only used actually if you want to train these things from scratch, right? So the initializers, what they do is they just put random numbers using a bespoke distribution into these things. This thing is particularly written for the T5 one, so I guess since we don't want to do initialization now, I would just propose we put also the T5 style everywhere and move on there. So that would be in line 116.
So since has initialized transformer feed forward network C, since we just decided that this is specialized to T5, should that be renamed as well?
Yes. So we could name the session as initialized T5 feed forward.
Has initialized T5 feed forward?
Yeah, that sounds good.
Okay. And I still don't understand why you don't want to automatically rename all of the occurrences, but instead do them manually. But sure, we can.
I think if we did this automatically, we would have thousands of errors at the same time. Here we get them one by one. So we can do this in the next thing we do, but right now I would prefer we do this manually.
Sure.
Okay, so a few more places and then we're done with that. Oops. Yeah, okay. And then we scroll down to, okay, so now we're in the forward function where we see some problems. Yeah, so this is obvious what the problem is. I think we also need T5 there. I
don't get an updated list of errors. 22 save or something? Because it still points me to the first place where we renamed the constructor to T5 forward network. So
I see the error in line 261. Maybe I can just fix it myself quickly. So it's just adding T5 here.
Okay.
Right. So now I get a bunch more problems here.
I don't see the errors, so you'll have to tell me. You'll have to describe the error to me in which line it is.
Okay, maybe I fix them just quickly myself because it's again T5 adding.
Sure.
So this is a bit boring. Initialize. What did you use? Oh, that's because the constructor name has changed too. Okay, I resolved all errors in this module, it seems.
Cool.
Of course, now downstream is stuff broken, but otherwise I think we're good. So I think what you could do is you could just copy paste now the instance as you wanted to do already 10 minutes ago.
Sure. so what is different about this instance? This is for BART. Anything else? We also need to put the layer norm at the end. I would have expected to have to change a bunch of things about the width bias in order to correspond to the changes we've made elsewhere. Are those taken care of automatically?
Yes and no. I think the problem we have now is that you still use the T5 type constructor there. That won't work. And you also need to rename the fields afterwards.
Okay, I don't see the squigglies, so again, you'll have to tell me what the errors are.
So far you're good on track. It all makes sense. Okay, the last one it doesn't like, but this is because Jello is not in the scope, I think. Do we have
so
Jello?
that's where we have to determine whether HaskTorch already supports Jello, and if so, import it.
So HaskTorch does support Jello, but my fork of HaskTorch does not.
Okay. So it's time to merge master into your branch.
No, it's more time to. So like when I say fork, I mean I made this gradually typed API, right?
Mm-hmm.
And I added things by need, right? Because the surface area of these Torch APIs is crazily large, and I didn't want to implement lots of things without need or cause. But we can, I think, add our Jello thing very easily. We just need to go to nonlinear activation.hs, I believe. No. So we go to activation.js. Yes. This is in neural network functional activation.hs, also in the gradually typed folder.
Neural network, what? I don't see an obvious way. Oh, right. I can click the pin to go where you are. Okay, activation.
Cool. Do you see Relo there?
Let's search for Relu.
Yes.
Yeah. So
cool.
presumably
so there's some others.
Paste that.
Yes. Well, I think you. Oh no, that's good. Yeah. Mm-hmm. Yep. Yeah, I don't know if this Jello _t exists. But it doesn't complain, so I guess it exists.
Presumably the documentation needs to be changed?
Yes, and I also don't remember what Jello actually does. Oh, Gaussian error linear units. Right.
Gaussian
so
what?
writing documentation for that is probably out of scope for this because math is not as easy. How about you just remove the math portion of it and just write, or either just write Gaussian error. What is Gaussian error linear units?
Mm-hmm.
Yeah.
Excellent. Oh. Yeah.
There. There is a description in the PyTorch documentation, but let's skip this now. We can do it later. Or
Okay.
I can do that offline.
So back to feed-forward network. Again, I can't see the errors. Is feed-forward network all good now?
No, we need to import it. For some reason,
since I don't see the errors, I don't see the quick fix either. There's probably a way to reset it somehow.
Yeah, that's weird. I could try to restart the Haskell language server.
But you're seeing it on your side correctly, right? It's just not
I see, yeah.
sharing with my side. But yeah, maybe restarting the Haskell language server might help. Is that something that takes a while?
It's already restarted,
Okay, cool.
and it's done now.
And it didn't help. I still don't see any error on Jilu.
Unfortunate. Do you still get type annotations when you hover over things?
Yes, I do know the type of Jilu, which means that you've already imported it using the quick fix, presumably?
No, I was just about to do that. I did now.
Oh, the type signature, the unhover type information just changed, which makes me think that previously it was not looking up Jilu and telling me the type, but rather like inferring the type from the context.
Okay.
There was an any in there, which seemed unlikely.
Yeah, any is not good.
Mm-hmm.
Okay, so we have a bit of a problem here. So the last bit there is, for me, underlined squiggly with squiggles.
Okay.
The problem is that the types have changed such that the computation that is wrapped into this feed-forward network output shape thing in line 316 is obsolete. So you can see that, so the way this is wired here, you can see that output, that there needs to be a proof, right? That output is this particular tensor here with gradient, with a certain layout, with a certain device, with a certain data type, and then also with a certain shape. And the shape computation is outsourced to that feed-forward network output shape type family, or maybe type synonym, I don't know. But this is the one that was appropriate for T5, right? Now we're using the formulation for BART, so we moved around the layer norm. We changed how these linear maps work from without bias to with bias. The activation function hasn't changed much. I mean, at least not for the types, because they had exactly the same type signature. But
So we need to
many other
copy
things have changed.
this type synonym as well. I guess we should rename it to T5 feed forward network output shape.
Yeah, that's good. Cool.
Copy it. Well, I guess before I copy it, we should find all of the occurrences. You sure you don't want to rename this automatically?
I don't think it will be in a few places. It would just be in one place, I think.
Okay, so let me try the magic of modern IDEs. Rename symbol to be T5, blah blah. And
I'm scared.
it didn't do anything.
Cool, then it's broken. Sometimes that happens. Maybe it's because your Haskell language server has some hiccups there. I will just do it manually again. Whoa, we also did it. T5 to 5.
Did it. Okay, so it's used.
Right, so this needs to be running. Oh, yeah. And then we need to make a new one for BART.
Yes, this one will be named BART.
Can you capitalize it, please?
Sure.
Thanks. Okay, so this thing doesn't exist yet, but I think we can build this off the template that we already have. It's not that difficult.
Okay.
Cool. So
yeah, I remember that at the type level, you need to repeat the shape of the value level computation, or at least the parts which involve some type level parameters, because since we're in your special gradually typed branch, you wanted to type check the dimensions where we know the dimensions statically, and delay to runtime the check for those dimensions which we do not yet know statically. And that involves a bunch of type level computations that we worked together for many weeks. So I would expect...
So
Yeah. Well, I would
ahead.
expect the same. Okay, well, first of all, there's the without bias that we need to change everywhere, but I would also expect something corresponding to the change we did to move the layer norm to the end. I just don't see
Yeah.
layer norm
So,
in there.
so I would suggest to make this a bit easier for you, cut it from there, the whole thing, and move it down to where the BART diagram is. Yeah, so it's just in between these instances.
Mhm.
Thanks. So, so we know that
Oh wait,
we know
this
that
one
the
is
first
T5? Did I just forget to rename it? Yeah, I just forgot to
you
rename
may have forgotten to rename it. Yeah. Okay. So I see less errors now. It's a good sign, but we're not there yet. So let me explain to you. Can we go back to the other one, to the T5 one above, and let me explain to you how these type families that are in it actually come about. So basically, the most inward thing, so the most deeply nested type family here, it's this
Mhm.
layer norm without bias thing, right?
Mhm.
And this is the most inner nested thing because it is the first thing that happens, right? So like you
Mhm.
go in with the query, and one of the type families is actually the query shape, right? And then afterwards you have the first linear layer, right? So like the output of the layer norm is what goes into the linear layer. Therefore, the output of the layer norm type family is what goes into the linear
That's where
type
the
family,
layer norm is. Okay.
right? So like since we moved the layer norm to the bottom, it needs to also go to the top level of that call, right?
Makes
So like
sense. So, except that each of those things take 2 arguments, which makes things a little bit more
yes,
complicated.
that is the case because now we have with bias, and guess what that extra parameter is for?
Uh,
We
what?
can do that later. Let's just get the order right first.
Okay. So, linear with bias f itself takes 2 parameters. I am guessing that this query shape becomes the second parameter of linear with bias f,
Mm-hmm.
and that
It's good.
I need to put layer norm at the outside most around broadcast. I don't remember seeing broadcast anywhere.
Yeah. So broadcast is because of add.
Okay, so
So
after the and.
yeah. So to just explain to you broadcast a little bit. So like without broadcast, you only ever be able to like add, multiply, divide, or whatever element-wise. Tensors have exactly the same shape. Broadcasting allows you to add, multiply, divide, subtract tensors of different shapes. But there's some rules to that, meaning, well, I mean, this is tantamount, but like I can say, then it needs to be broadcastable.
Okay.
So the broadcast shapes F type family just handles these rules. So there's a check involved. Are these two tensors compatible? And if they are, then the output shape is computed based on these broadcasting rules. So for instance, if you have a tensor that has just one element, you can
Oh,
add
like
it
scalar
to
product.
anything.
Yeah. Okay. Cool.
Yeah, so
Um,
it looks a bit weird now because I think
well,
of
yeah,
the
the indentation is
indentation.
weird. So I was waiting until you were done with your explanation to ask if there is some IDE magic to reformat it the way you like, or if I should indent
Yes,
it
you
manually.
press tab. Oops, wait. Uh, oh, okay. No, sorry. Press, go to the context menu of everything. So like basically right click and choose format document.
Excellent.
That did something. Yeah, I think it worked. So this uses, I think, or Molu, or Molu. Oh, I don't know how to
Mm-hmm.
pronounce it. Or Molu. It's the format I think Tweak made. Was it Tweak? Yeah.
I don't remember who made it.
Um, anyway, so it's auto formatted now. But for me, I have tons of squiggly lines because nothing is in scope. So I have to add this stuff into scope real quick.
To add what into scope? Just to reorganize the things around?
Yeah, so the layer norm with
Oh,
bias.
the width bias thing. Okay.
Yeah, so these things were not in scope.
Okay. But you will
And
have to do the quick fix because I don't have access to it anymore.
wait a minute, something is off in the other one though. Why did that happen? Oh, could it be that you? I think you may have deleted something there.
Oh, the other one meaning that the T5
Yeah,
feed forward.
Yeah.
Network
So now
output shape.
every pad there was something was afoot there. I used the backward, so like I removed that change using the IDE. So, but it's still complaining, and the complaining happens because we call in that type family with two little arguments.
Which type family?
The linear with bias type family.
Because we need to give it something about the bias.
Yes.
Okay.
So I can do that quickly for you. I believe this would be appropriate. And then in the same fashion for the other one. And if not, then a linear layer norm with bias is also in need of a second annotation. And I think it would be shape query. Right. So I hope this works now. Yeah, I think we have less type errors now.
All right. Where's the next one?
So the next one is the next one is funny because it has to do with the type level rewrite rules plugin.
Ah.
Yes. Okay, so for me it says that there are two kinds that are, types actually that, well, I think they're kinds, but this thing tells me the types are not the same. So we have in our output must be tensor blah 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 thing something about query data type and data type, right? So the problem I have here is that JC insists that the order is wrong. So that actually data type comes first and query data type comes second. So what I would propose is that we quickly change the order and see if this resolves the issue.
Change the order of what? The typing, the rewrite rules, or the order of the code you just wrote?
No, not of the code that we just wrote. If you go to line 335, could you change the order of these two things? First data type and then query data type.
Okay.
Looks good. See, this resolved one issue, but we have another one. Can you do the same for the layout, please?
Okay, I don't understand what I'm doing, but I'm doing it.
I'm just following the types.
Okay.
And now we have to do the same with the devices. Let's see. So
There's
first
three.
we have to say device, I believe. Yeah, and then second we need to say, something else is now wrong.
Was the second supposed to be query device or generator device?
Match. Got it. One moment. I need to parse this. This is a bit more involved.
I guess while it's loading, maybe I can explain the context. So before we decided to work on this Haskell mask project with the reconstructing Haskell code, Torsten and I were pairing on HaskTorch, a different part of the project, where we were using the type level rewrite rules package that I've uploaded to Hackage a while ago, and investigating why it was not working on HaskTorch. So, type level rewrite rules is a project that I've uploaded to Hackage for solving the following problem, that sometimes you have an expression that is equivalent to another expression, like in this case, n plus 0 is just n, and in this case, m plus n plus o is the same whether you put the parenthesis on the left or on the right, in the sense that it will result in the same value, but GHC doesn't know that this is true because GHC doesn't know a lot of information about plus. And there are some type checker plugins that do know about plus and that will discharge those specific constraints for plus specifically. But type level rewrite rules is more general than that. It allows you to write your own. And so Torsten wrote his own, and that did not work. And so we spent a lot of time debugging together, and eventually we realized that I did not know what I was doing when I wrote type level rewrite rules originally. And so we learned together what was the proper way to do things. And so now we have the ability to write code like this one, with those pluses. If I go to the definition of plus, yes, so this is a type family around unify, and unify is defined here, and unify is similar to plus in my previous example. Like, you know that n plus 0 is the same as n, but GHC doesn't know, but we can teach it that. And so similarly, there's a bunch of rules. Where are they listed? Is it in this file? Yeah, here. There's a whole bunch of rules for simplifying unify. Like that, for example, that associativity, same thing as the A plus B plus C example I just showed before, but also that unify of A with A and B is the same as just unify of A and B. So it's idempotent. So there's a bunch of simplifications here that allows us to write a type expression here that is much shorter than having to repeat the entirety of the value level code at the type level. And so because of that simplification, it's easier to follow the type in order to figure out what should be there. But clearly that is not working out. So Torsten, I see you're modifying some code. So did you figure out the problem?
Well, the thing I'm struggling with, I don't even know where exactly the problem is. Like, I don't know if which part of the, I have two, okay. So there is the generator device and there is the device of the tensor and output, right? I don't know if the error I'm getting is for the generator output or for the tensor itself. And the error message is not really helping. Because it's like this wall of text.
Despite the fact that we worked together on type level rewrite rules to improve the quality of its error message, including by making it point to the right line number, it's still not helping?
Well, the line, I mean, the error is thrown in 354, right? But the cause of the error is in the instance bounds, right? Okay. So I don't know which instance bound is now responsible, which I have to modify here. For this error to go away. There are two choices. One is line 334 and the other one is line 337.
Okay, just stop messing with the code and put it in a reasonable enough shape because I suspect that I only have one shot at clicking the button to show the error. So I don't want to see an error that is not the one that we will be looking at together for the next several minutes. So is the code stable now?
Yeah, I'm not changing anything right now.
Okay, I'm clicking on the button to look at the error. Now we can finally look at the error together. Okay, so it is indeed several pages long. And what does the error say? Can I make that bigger? Okay, so first of all, I see that blah 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 does not export, has initialized blah blah blah. Presumably that's not the one you're looking at. Another does not export blah blah blah. And then I have couldn't match type unify blah 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 blah. Pages and pages and pages and pages and pages.
Yeah.
Okay. I don't even see what it doesn't unify with. I think I scrolled down too much. So you're saying it's not possible to copy paste from this pane?
No, I didn't actually try from that pane. I tried much more painfuler copy from the pop-up menu I get when I hover over the squiggly line.
Okay, so...
And that was, yeah.
I want to just open a new file.
The thing is also like in that problem section down there, we have lost all indentation, and this makes it much harder to read.
I thought I copy-pasted the error message, but instead it's pasting some JSON?
Is it? Interesting.
Oh, okay, I know why. Okay, so that's because it gives me a bunch extra information, but the error message is in this very long line. It's just a very long string, I think. How many characters? 8,000, yeah, that's probably all the information. So...
Okay.
Well, you think this is useless, but it's actually good. So I'll copy this very long string, and I will use... I don't yet know how to use the terminal inside the Visual Studio, so I will use...
we could also use Cabal, right? And just use JCI to study the same error, if that helps.
Okay, so I have this put strlen command line program that is very simple. It just calls read on the string and calls put strlen so that we have the same string without the quotes and like the \ns interpreted and so on. So now we have the whole string and it is indented. So I think we'll be able to work a little bit better. So couldn't match type this thing with that thing, arising from a functional dependency. I did not expect a functional dependency. Between the constraint has forward blah blah blah.
Oh,
that's very long. Arising from a user forward.
So what I've noticed is because I have these functional dependencies, Haskell is actually doing a lot of work for me, especially if I use like these forward things, right? Mm-hmm. Because every instance of HashForward has functional dependencies, right? So like if I compose those, the functional dependencies will figure out the types for themselves usually. Mm-hmm. It's just that in this case here, I need to tell Haskell what the function, to fulfill the functional dependencies, I need to tell Haskell what output and generator output are. That's why I have these bounds. So typically the way I did this is I would just not do it, look at the huge wall of type errors and just copy paste what Haskell thinks the type is, mm-hmm. and then simplify that type as much as I could, mm-hmm. right? So this was my workflow here. So now, of course, we made changes to this, and this invalidates probably some of the simplifications I made along the way, and therefore we're in this dilemma right now. So maybe if you went to that arising from functional dependency block and looked at what it actually wants these device types to be, we can maybe get a clue of what's going on and what we need to put in there to make progress.
So let's see. So has forward, how many arguments does it even have? There's one short one here, there's one huge one here, and there's one huge one there,
so
and
we're
there's
looking...
another one there, and there's another one there. It has like 5 arguments. Okay.
Right, so the has forward of the layer norm is that thing that throws the error right now.
Has forward of the layer norm. Okay, yeah, the first argument to has forward is layer norm, okay.
So it should have 5 type arguments, and actually we're interested in the last 2.
Okay, so 1, 2, 3, and then the last 2 are this huge tensor and this smaller generator. Yeah,
so bear with me, I'm 20 seconds behind with regards to your screen, because I'm watching you on Twitch. Wait, so where are you now? So you're in...
I kept moving around after you told me to stop doing so. So now I'm stuck.
So I'm interested in the 5th type right now. So
okay,
there
5th type is generator. There you go.
Generator, but then the argument is device, and what's next?
The argument to generator is torch.gradually type.unify of device type nat. That's the first argument to unify. The second argument to unify is device, and the third argument to unify is a nested call to unify. I guess I can ignore the first argument to unify. It's always device type nat.
Exactly. So actually,
I think I can
if you squint, you see that it's just device followed by query device followed by generator device, which is exactly what we already have. So that's not the problem. It must be the other device. So if you scroll up to the 4th argument, the one that is a tensor, and look what the device there is, I think we find the culprit.
Okay, so this one says tensor with gradient of unify of layout dense union query layout unify of device union unify query device union generator device, and then unify data type union query data type, and then layer norm with bias shape broadcast shape query shape linear with bias shape. There's no more unify in there. So is it one of those 3?
Yep, must be. But it must be the device, right? Because this is what the error said. Couldn't match something unified device, crucially nested blob with what we have already written there. So I'm a bit confused actually, because it seems like Haskell on its own comes up with the thing we already have, but still rejects it. I don't know why. So this is all right associative, right? So like if I were to put parentheses around these things, it would always be to the right, right? So like this. No? I'm making changes on the file, so here is my change. So just change nothing, so that gives us a good.
I'm trying to get both visible at the same time. Oh, I know. I can put that on the right, and then put that here. Okay, so now we can see both. So we have tensor with gradient of layout dense union query layout, and device union query device union generator device. That's the same as well. And data type union query data type. That's the same as well. Okay, so those 3 are the same indeed, but you expected them to be different because could match type, that big thing. with some small things. So I guess we should simplify the error message as well. So unify of that, unify of that becomes, I guess I should use the plus notation. Wait, I deleted too many things. Let's do one thing at a time. So unify, this one takes this argument plus the next argument. And then we have this nested unify device plus rest. And now let me showcase some other cool transformations. If I remove the quotes so that all of this is a valid show instance, I can call shower to reformat it. Okay, so that's more readable. Let's keep going. I remove this unify plus that one, this unify is this argument plus that one, this unify is that argument plus that one, shower. Okay, so it's complaining that it cannot match device plus query device plus generator device plus device plus query device plus generator device with something else. I'll simplify that as well. Unify of device plus something else. Of unify of query device plus something else. Okay, so we wrote device plus query device plus generator device, but it expects device plus query device plus generator device plus, again, another copy of device and another copy of query device and another copy of generator device. Okay. So now I'm wondering if that might be a problem introduced by the type level rewrite rules, right? Because we've seen that before, in which there was code where the code written and the code that the error message says it expects is the same, which seems to be the case here. But the reason it's not, the reason there is a type error is because the type level rewrite rules plugins has rewritten the code that we wrote into something else that doesn't match. However, I would expect that to only rewrite it to simplify things, not to make things bigger. So I just want to look at the rewrite rules that fired in order to eliminate that hypothesis. So here, same thing as usual. Simplifying to make it more readable. Like this. So there's a rewrite rule that rewrote a plus b to just a plus b. That's one of the rules we were looking at earlier, that a is idempotent. And that's the only rewrite rule which fired. The rest is just giving us the context. So that's not... oh, that might be to blame, actually, because what we have here... no, it's not... It doesn't have that shape. Let's see. A plus B versus a plus b. Whereas this is just like C plus another copy of C. Like if I lay it out like that. Oh, it's not actually the same. The parentheses are different. So I would have expected type level rewrite rules to simplify that further. Why didn't it? Mysterious, mysterious.
Indeed.
So where is this A plus B plus C plus A plus B plus C, but with different parenthesization coming from? It says arising from a functional dependency, but I don't yet understand that part of the code. What, like, I guess the definition of has forward has a
yeah, so
type
I mean,
family
you know what I will
functional
do
dependency?
now? Like maybe you can make progress actually by playing dumb. Making changes in VS Code right now. I don't know if you can see
Yeah,
those.
I can
If
see.
I just force both to being unit, right? We get very less of, I mean, we get much fewer confusion about types now, right? So like it will give us the whole block now, and I will just go and stupidly paste this thing in. I'll do this first with the generator. And I will just import that thing now. And then I will do that for the other thing. So now we have these things completely expanded, and it looks awful, but the type error is gone, which is good. So there is
Excellent. So now we can
consistency.
just simplify. Cool.
we could do it by hand now and see where this faults apart.
Well, there's a lot of code to generate, but there's two of us. So you want to tackle output, and I'll tackle generator output?
Yes, so I can do the upper part, no problem. I think it's easy because we already did a lot in this other thing. So if I replace the shape with the BART feed forward network output shape type synonym, that goes fine, no error. Then I think I can just do this. So I just copy paste what I already up there, and hopefully nothing. Right, so it looks like the problem is the generator part.
Because you already did your half and
Yeah,
did
I'm
not
done with
encounter
mine. That's exactly, yeah, I'm done with mine. It's exactly the same as it was before we started doing this. Okay, so no error on my side. I will just format your code.
Yes, that's what I was about to do. Okay.
So maybe there's just no rule for this, right? So like I've written hard rules for up to 8 levels of simplification, but maybe this is just one too many here.
Well, let's try to apply the simplifications by hand. No, I'm trying to get rid of it. Not okay. Close. Okay. I'm just trying to give myself more room. Okay. So we know that Unify is made right associative by one of the typing rules. If we ever see something like this, in which the parentheses force it to be left associative, the typing rule will rewrite it to be right associative, like that. So that should still
Still no
work.
error. Oh, we got an error. We got an error. We got an error.
did?
We got an error. Yes. Yeah, so it doesn't like what you just did.
I don't see the squigglies, but I will undo what I just did.
Can you maybe work on the other branch and see if this...
So same thing here. It's left associative. I should be able to move the parentheses around here. Does this also break it?
This breaks everything again, yeah.
Okay.
Can you delete the first device? No.
So any simplification we perform seems to make things worse for some reason. Let's see. Okay, these parentheses.
Can I choose the auto format? This pains me.
Well, I just reorganized it so that I could see what was going on.
Yeah, but like you missing that this thing here is nested, right? So like you would have something like this, I guess. Right. So this is there. Oh, let's just move it on the same line, actually. There. Right. So we have device, 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 and then somewhat readable, I guess. So I guess it cannot do the...
Well, let's see. So this says that we are assuming that generator output is equal to generator of blah blah blah. And given this assumption, it type checks the instance. So somewhere in the instance, we are making use of that fact. But the rewrite rules, they are only going in one direction, right? They are rewriting the assumptions to be right associative, and they are also rewriting the places where we need something to be true to be right associative so that they both line up, right?
Mm-hmm.
So so there is something in the implementation of forward which currently requires this, and it does not get rewritten. It's not this that does not get rewritten, it's the place that requires this assumption that does not get rewritten to the simpler thing we want to write at the top. So I think that's where we should be focusing on our effort, figuring out where that code is and why it does not get simplified. Or wait, no, you were saying that you think that maybe the rules don't fire on this either, which would need to be the case elsewhere as well. So maybe we can create a standalone function.
Yeah, so we should
expression.
probably... Yeah, go ahead. I know what you're doing.
Okay, so
put it at the
function...
end. This.
What?
I mean, where are you now?
297?
Yeah, that's okay.
Okay, so we... if I assume something about that, I should be able to conclude... wait, no, that's much easier than that. I can say that this... I can ask that this whole thing is equivalent to... well, the next thing we want. So, for example, a version in which the parentheses are to the right, And foo can be undefined, I don't care. This is just a function.
Yeah, but this all has type checks, right? Because you never need, I mean, you're putting this as a given.
This is the first step. And then
Okay.
bar does not make this assumption. It produces a unit by calling foo. So foo needs this to be true. And in order for bar to type check, GHC plus the type checker plugin needs to be able to discharge this type level equality. And clearly it is not, because it's saying
bar and but. That's
okay.
Okay, but it likes
it is discharging it. Okay, so that is not the problem.
Okay.
Type level rewrite rules is doing its job. Okay. So that is not helping us make forward progress.
Wait, why don't you like make more changes to it now? Yeah. Like, I mean, can I make a change that I hope will at least. I mean,
we want the whole thing to be
eventually
device plus query device plus generator device, right?
Yeah, exactly. So like, sorry. Okay. Let me just mess with this quickly. So I would assume that this won't hold because we're seeing that this produced the error down there, right? So like, if I just do what I think eventually will be needed here.
Yeah, I think this should work.
Wait a minute, I made a parenthesis. Oh, I don't need this parenthesis? I don't. This works.
Mm-hmm. So type level rewrite rules
this is unexpected.
is doing its job. So what's wrong then?
Yeah. Is there no stupid spelling error down there? No. What's the problem? You know what? So, I mean, we can get around this problem by just giving this as evidence. I hope. No, not even that works. What the?
So you're adding.
I'm adding the thing that you had in your foo thing as evidence.
Because that's what the error message says. It says, oh, I have plenty of older versions of Visual Studio Code open. Okay, now I have on my phone. Okay, so yeah, the error message is saying that device plus query device plus generator device plus device plus query device plus generator device is not the same as device plus query device plus generator device. So you think that even if we write that down, it will not be accepted?
I just don't understand what's going on here. So like, I thought if I say that this here that holds and I put as a given, then I can go ahead and comment this and put this here instead, and then clearly this must type check because now it can go back and forth between the two things, but it doesn't like that. So what's going on?
So one more time, please. So you had generator output equal generator foo, and foo is tilde equal to bar. That did not work, or that did work?
Right now I'm seeing a type error.
I'm just trying to understand what changed. So before things did work, before you changed on line 362, before you replaced the left-hand side with the right-hand side, it was working, right? Okay. That is indeed curious.
can I actually use type variables here? Can I just say this is A? This work? This does work. Can I then also say that A is this thing? No. What the heck?
But wait, the error message is different.
Is it?
It's no longer
Reduction
saying...
step overflow. Wow.
Yeah, we're familiar with that because we changed together the behavior of type level rewrite rules so that instead of having an internal limit, it now uses GHC's limit.
Mm-hmm. Wait a minute. So I'm gonna change this again quickly. Let's open the Cabal file.
So that makes sense actually, right? If there was in the instance, if there is something that requires generator of long expression to be satisfied, and it has in the context generator of long expression, then GHC will directly eliminate the given with the wanted, and everything will type check, and we will not even reach type level rewrite rules. But if the wanted is generator of complex expression, but the given is generator of simple expression, then GHC says, those don't look equal. I can't proceed, but before producing a type error, it asks type level rewrite rules or any type checker plugin that is enabled for the file if they can make sense of what's happening. And so it's only in that case that type level rewrite rules is going to try and simplify step by step. So it makes sense that the change you made would cause things to fail with a stack overflow. But I am hoping that if we increase the limit, then it will still work.
So I looked into the Cabal file, and f constraint solver iterations is set to 0. So does 0 mean use the default, or does it mean no limit?
No limit, which is dangerous. You like to live dangerously. So why did it use 200? Could it be that that when you build with Cabal versus when you build with Haskell language server, that it uses different limit or something weird like that? Like if you just type Cabal build in a shell, does it succeed or does it fail with the same error message?
Now, I would assume that the Haskell language server is the Cabal is the ground truth for that, right? Source of truth for that. Yeah, so I'm getting use reduction depth equals 0 to disable this check. I have a different parameter here. I have constraint solver iterations. So we have a different mechanism here that is running out of fuel. So I will not do that globally. I will just add this to the module's header. Can I just do options GHC twice, or do I need to put this in the same? Okay. Okay, I did add this now. And yeah, I'm running out of memory. Yeah.
Okay. So
no, wait. I mean, I don't know what it's doing now. Actually, I think it survived.
Oh, really? It just took a lot It took a lot of memory.
No, I'm having.
But it compiled?
No, so like the Haskell language server is sitting at 250% CPU, but it's not having a space leak as far as I can tell. It's just not finishing.
Okay. Well, it's easy to accidentally cause loops with type level rewrite
Yeah.
rules if we write two rewrite rules that can rewrite to each other. So maybe that would be another thing that we could look at. But how about looking at that next time? We've been at this for a few hours
Yes.
already.
So I will just commit this with the clumsy,
Mm-hmm.
unsimplified version, and just leave this for next time. Cool, but
Great.
it was fun. We managed to do one little piece in a big puzzle, but I think we're on track.
Great. So let's do this again. And see you next time to fellow Haskellers in the audience as well. Ciao.
Ciao. Have a nice day.